Hello everyone, this is Fatima, a final year undergraduate at IIT Bombay. Today I'll be presenting our work, Regret Optimal Online Caching for Adversarial and Stochastic Arrivals. This is a joint work with Priya and professors Nikhil, Karamchandani and Sharayu Moharir. The caching problem has been studied since the 1960s. At the time, the problem was motivated by memory management in computers. In recent years, a lot of the work on the caching problem has been motivated by content delivery networks used for applications like video on demand services such as Netflix and YouTube. The basic framework for the caching problem is that we have a library of L files. The cache can hold at most C files. Requests for arrivals arrive sequentially. If the requested file is present in the cache, we say that a hit has occurred, and we say that a miss has occurred otherwise. The algorithmic challenge is to determine which file to store in the cache over time, and the goal is to maximize the number of hits or equivalently, minimize the number of misses. Time is divided into slots. In each slot, we first have a request arrival for one of the L files. If this file is present in the cache when the request arrives, we have a hit, else we have a miss. Our caching policy then makes a caching decision, that is, it decides which files to store in the cache. We assume that before the next slot begins, the cache is updated accordingly. Two types of arrival patterns have been considered in the existing literature and in our work. The first is known as the independent reference model, where request arrivals are generated by an IID stochastic process. Since the focus of this work is on online caching, the distribution of the request process is unknown to the algorithm, and further, requests are revealed causally, and therefore caching decisions have to be made based on past arrival patterns without any explicit knowledge of future arrivals. The second arrival model is the adversarial arrival model, where we make no structural assumptions on the arrival process. Here, the arrival pattern is generated by an adversary who has knowledge of the caching policy being used. However, in case the caching policy is randomized, the arrival sequence is generated without the knowledge of the exact sample path of decisions made by the policy. Here again, since we are focused on the online caching problem, caching decisions have to be made based on past arrival patterns. Various metrics have been used to characterize the performance of caching policies, including hit rate and the competitive ratio. Recently, regret has been used as a metric for the online caching problem and is also the performance metric that we use. For the IID stochastic arrivals case, our benchmark is a static policy called OPT, which caches the C most popular files. The popularity of a file is defined as the probability of an incoming request being for that file. To implement OPT, we need to know the distribution of the arrival process. For each candidate policy P, regret is then defined as the difference between the expected number of misses under the candidate policy and the expected number of misses under the optimal static policy. Note that this is a measure of the performance of the candidate policy in expectation. For the adversarial arrivals case, our benchmark is the static cache configuration, which maximizes the number of hits in the first capital T time slots. Note that this policy can be implemented only if we know the entire arrival sequence a priori. Let A be an arrival sequence and P be a candidate policy. We first compute the expression in red. It is the difference between the number of misses under policy P up to time T for the arrival process A and the number of misses under OPT up to time capital T for the arrival process A. Regret is then defined as the maximum value this difference takes across all possible arrival sequences. It follows that the adversarial regret is a measure of the worst case performance of the candidate policy. In this work, our goal is to determine if there exist caching policies that have order optimal regret with respect to time for IID stochastic and adversarial arrivals, and therefore robust in the nature of the arrival process. Many times, policies that do well in the adversarial setting are primarily focused on not performing very badly for any arrival sequence. This often leads to suboptimal performance for specific arrival sequences. Similarly, policies designed for specific arrival sequences or under some structural assumptions in the arrival process have poor performance in the adversarial setting, as they have very poor performance for specific arrival processes, which affects the worst case performance of the policy. Therefore, a policy that is order optimal under both adversarial and stochastic arrivals is desirable. I will now present two popular caching policies. The first is least frequently used, also called LFU. To implement LFU, we need to keep track of the cumulative number of requests for each file and the set of files currently in the cache. Under LFU, the score of each file is the cumulative number of requests for that file thus far. In each slot, the cache is populated with the C files having the C highest scores. For example, if C equals 3, LFU will cache files 6, 8, and 9. Note that LFU is a deterministic caching policy. The second policy is called the follow the perturb leader. Here again, we keep track of the cumulative number of requests for each file. Under FTPL, the score for each file is the sum of the cumulative number of requests for this file and a random perturbation. In the stock, the random perturbation is a zero mean Gaussian random variable with a suitably defined standard deviation denoted by eta t. In each slot, the cache is populated with the C files having the C highest scores. FTPL is a randomized caching policy, and the source of randomness is the zero Gaussian perturbation with standard deviation eta t. The performance of FTPL depends heavily on this standard deviation, which is also called the learning rate. So in this particular case, FTPL would cache the files 2, 5, and 6. Here is an overview of what is known about these two policies. LFU is known to have order optimal regret with respect to time for IID stochastic arrivals and is known to be strictly suboptimal for adversarial arrivals. FTPL with eta t proportional to square root capital T and eta t proportional to square root small t are both order optimal for the adversarial setting, with regret scaling at order square root capital T. Note that capital T is the number of slots in the time horizon of interest, while small t denotes the index of the current time slot. Recall that the question we are trying to answer is, are there caching policies that have order optimal regret with respect to time for IID, stochastic, and adversarial arrivals? Since FTPL is already optimal for adversarial arrivals, we make an attempt to characterize its performance for the stochastic setting. Our first result characterizes the performance of FTPL with a constant learning rate. That is FTPL with the variance of the Gaussian perturbation being time invariant. We show that for IID stochastic arrivals, if the learning rate is constant, the regret scales at least as square root capital T. Since LFU has constant regret for IID stochastic arrivals already, we conclude that FTPL with a constant learning rate is strictly suboptimal for this arrival model. Our next result characterizes the performance of FTPL with a time-varying learning rate, that is FTPL with eta t proportional to square root small t. We show that for this learning rate, the regret of FTPL for IID arrivals is a constant independent of capital T. We thus conclude that FTPL with eta t proportional to square root small t is order optimal under IID arrivals. Since FTPL with eta t proportional to square root small t is also order optimal for adversarial arrivals, we have a policy that is simultaneously optimal with respect to time for both arrival models. I will now walk you through the proof outline for this result. But before we get into the proof, here is a reminder of how FTPL works. The score of each file is the sum of the cumulative number of requests for the file and a random Gaussian perturbation. In each time slot, the files with the C highest scores are cached. We define mu I to be the probability of an incoming request being for file I. Without loss of generality, we assume that the files are indexed in decreasing order of the mu's. That is, if I is less than j, then mu I is greater than mu j. The key idea is to show that FTPL mimics the optimal policy with high probability. For IID stochastic arrivals, the optimal policy caches files 1 to capital C. Consider some file I, which is less than or equal to capital C, and some file j greater than C. OPT will cache file I, but will not cache file j. The expected cumulative number of arrivals for files I in the first t time slots is equal to t mu I, which is larger than t mu j. The expected values of the scores for files I and j are t mu I and t mu j respectively. We define event E as the event that under FTPL, the score for file I is greater than the score for file j. We obtain a lower bound on the probability of the event E and account for all the possible pairs of I and j. This helps us characterize the probability of FTPL caching the C most popular files, that is the same files as OPT. The way to account for all possible pairs is to use the union bound, which can be quite loose, especially for small t. To deal with this, we divide the interval of interest into two parts. For the initial t0 time slots, we upper bound the regret by t0, and for t greater than t0, we use the bound obtained above. This idea was proposed in the reference in the footnote. We optimize for t0 to obtain the tightest possible bound on the total regret at time capital T. This trick improves the dependence of the regret on the library size L from linear to logarithmic, which could be significant if the library size is large. Here are some simulation results illustrating the performance of FTPL and LFU. On the left, we have IID stochastic arrivals where both FTPL with learning rate proportional to square root small t and LFU perform well, while FTPL with learning rate proportional to square root capital T has regret that grows with time. On the right, we consider a round-robin arrival process with two files in the library. We note that for this arrival sequence, both versions of FTPL outperform LFU. This is consistent with the fact that LFU has linear regret in the adversarial setting. To summarize the results thus far, we characterize the performance of FTPL under constant and time-varying learning rates for IID stochastic arrivals. Note that LFU is equivalent to FTPL with learning rate equal to 0, that is, adding a 0 means 0 variance random Gaussian perturbation. It therefore follows that LFU perturbs the least and is optimal only for the stochastic setting, while FTPL with learning rate proportional to square root capital T perturbs the most and is optimal only for the adversarial setting. The takeaway here is that learning rate proportional to square root small t, which is somewhere in the middle, is simultaneously optimal for both settings. In the setting discussed so far, there is no penalty for changing the contents of the cache. Typically, to change the cache contents, files have to be fetched from the place where the entire library is stored into the cache. This increases the communication load on the system, and therefore it might be desirable to minimize the number of switches in the cache contents. We incorporate this into our model in two ways. In the first generalization, we restrict the time slots in which cache contents can be changed. In the second generalization, the system incurs a cost for each switch. Our goal remains the same. We want to find a policy that is simultaneously optimal for stochastic and adversarial arrivals. In the first generalization, we impose the constraint that the cache is allowed to change its contents only at S predetermined time slots. That is, the cache is allowed to change its contents at time slots 1, R1 plus 1, R1 plus R2 plus 1, and so on. We first consider the setting where all the RIs are the same, that is, the cache is allowed to change its contents only every R time slots. We first characterize lower bounds on the regret of any online policy for both arrival models. Further, we characterize the performance of FTPL with a learning rate proportional to square root small t for both arrival models. In summary, our results show that FTPL with a learning rate proportional to square root small t is order optimal for both stochastic and adversarial arrivals. We have also extended these results to the setting where the gap between the two slots in which cache contents can be switched is not necessarily uniform. Here we have shown that under IID stochastic requests, FTPL with a learning rate proportional to square root small d has order optimal regret. We now move to the second generalization. Here the system incurs a cost of d units for every change to the cache contents. We refer to the cost incurred due to changes to the cache content as the switching cost. We suitably update the regret metric to take into account the switching cost incurred by any candidate policy. Our first result is an upper bound on the regret of FTPL for stochastic arrivals. We note that, like in our original problem, the regret of FTPL with learning rate proportional to square root small t is a constant with respect to time. I would like to highlight that the bound on the regret increases linearly with the switch cost capital D. It thus follows that the performance of FTPL can potentially deteriorate as the switch cost increases. This is not surprising since FTPL does not take the switch cost into account while making caching decisions. Here we plot the number of switches to the cache contents under FTPL. Not surprisingly, the bulk of the switches happen initially when the scores of the various files is most susceptible to noise. When the switch cost is high, these initial switches can lead to significant deterioration in performance. To address this, we propose a policy called wait then FTPL. Under this policy, we have an initial wait period in which we make no changes to the cache contents. After the wait period, our policy makes the same decisions as the FTPL policy. Waiting too long will increase the number of misses incurred. On the other hand, not waiting long enough leads to an increase in the switching cost. To balance this trade-off, we set the duration of this wait period as a polylogarithmically increasing function of the switch cost capital D. Our next result characterizes the performance of wait and FTPL for stochastic arrivals. The regret of wait and FTPL with learning rate proportional to square root small t increases logarithmically with the switch cost capital D and is a constant with respect to time. Wait and FTPL thus has order optimal regret with respect to time for IID stochastic arrivals. Our next result characterizes the performance of wait and FTPL with learning rate proportional to square root small t for adversarial arrivals. The regret of wait and FTPL scales as square root capital T over here. Here is a summary of the results for the setting with switch cost. We characterize the performance of both FTPL and wait and FTPL for stochastic arrivals. The regret bound for FTPL for adversarial arrivals was already known. We characterized the adversarial regret bound for wait and FTPL. Both FTPL and wait and FTPL with learning rate proportional to square root small t have order optimal regret with respect to time for both stochastic and adversarial arrivals. For stochastic arrivals, the bound on the regret of FTPL increases linearly with the switch cost D, while the regret of wait and FTPL increases logarithmically with the switch cost capital D. Here we compare the performance of FTPL and wait and FTPL with learning rate proportional to square root small t as a function of the switch cost D. We note that as the switch cost increases, the performance of FTPL worsens at a faster rate than wait than FTPL. To conclude, we studied the online caching problem with regret as the performance metric. Our goal was to find a policy that is simultaneously order optimal for stochastic and adversarial arrivals. We showed that FTPL with learning rate proportional to square root small t is one such policy. Further, we generalized the above result for specific cases under the restricted switching setup. Further, we showed that FTPL can perform poorly in the presence of high switch cost. We proposed a variant of FTPL called wait than FTPL to address this limitation and show that the variant is also simultaneously order optimal for stochastic and adversarial arrivals. Thank you.